finding power series, right? Finding Maclaurin series for various functions. And so the process that you're going to do is you're going to find various derivatives all at 0. And then you're going to try eventually to find a formula for that guy. Because if you can find a formula for that guy, then your power series, your Maclaurin series, is simply going to be that and that are going to be fixed. So you see, the only thing you need to know is this guy, right? If you know this guy, don't you know the power series? Because it'll always, well, typically always going to be that over that. That's a factorial there, right? So the value of the function at 0 is e to the 0, which is 1. If I differentiate this, it's going to be -4 times e to the -4x. And if I find the first derivative at 0, it ends up being -4. A little bit quick there, but you're comfortable with it. It's really not anything too clever. Now, the second derivative is the derivative of this. And yeah, you get -4 times -4, which is 16, e to the -4, but don't write 16 down. Because if you write the calculation, you'll lose the pattern. So what I'm going to do instead is I'm just going to call it 4 squared, e to the -4x. Would you agree that the two negatives make it positive and 4 times 4 gets you 16? And so when I do the second derivative at 0, I get positive 4 squared. Now, here's the next one, the third derivative. Well, you multiply by another 4, and now you get this guy. And the third derivative at 0 ends up being -4 cubed. Now, depends on you. Sometimes you need to do more, but I think I can see a pattern. Does anybody want to tell me what the answer that goes here is without doing anything else, just using these numbers, these answers here, and detecting a pattern? What would the next one, the fourth derivative at 0, be?
-4 to the fourth. Sorry, +4.
+4 to the fourth. Let's see what the patterns are. Do you see that? Okay, that one's a special case, but don't worry about that. That'll sort itself out. -4, +4 squared, -4 cubed, +4 to the 4. Agreed? And if you check it out, you nailed it. Now, if you can do that, you should be able to do this. Now, what you've got to remember, that one tends to distract me, so I just start here. 1 gets you this, second derivative gets me that, third derivative gets me that, fourth derivative gets me that. What would the nth derivative be? Basically using the same pattern, but generalizing a little bit more.
-4 to the n.
Do you want negative? We'll do that. I like the 4 to the n, but I want you to focus on it. If you put negative there, aren't you saying that all the answers are negative? And you know that's not true. So I think what you're hoping is it's going to have -1 to the power, isn't it? That's what you meant, right? Now, you've still a decision, but only 2 things, n or n plus 1. That's the 2 I like to pick, right? I mean, right? Is it n or is it n plus 1? Which one generates this pattern?
N.
Agreed. And couldn't you just check it by looking at the third one? Yet negative, second one positive, right? It's easy to do. Which means we have solved our first question, because the power series for e to the -4x is n equals 0 to infinity, the nth derivative formula, x to the n over n factorial. And someone yesterday asked a very good question. They said, should I style points combine these into a single 4x to the n, right? And the answer is no. The convention is that power series, you should have the x's to the n, the x's to the 2n, you know, the x to the 3n plus 1, whatever it is, but it should be on its own sum, right? And that's finished. You now have a power series for e to the negative 4x. So do you see it's a fair amount of work, isn't it? And it's mostly pattern recognition. And one of the clues to doing or to getting it right is never do a calculation. Write down what the calculation is, but don't do 4 cubed is 64, right? Just call it 4 cubed. And don't do 2 times 3 is 6. Don't write 6 down. Write 2 times 3, because maybe the next one's going to be 2 times 3 times 4. Do you see a factorial would be appearing? And that helps with the recognition. So let's do this fella. Question 8. If you do that guy, you get 8 to the 0, which is 1. Right? If you differentiate 8 to the power of x, you get 8 to the power of x. Do you get anything else? I'm phrasing it in a way that the answer is yes, you do get something else. What do you get? Ooh. We don't differentiate 8 to the x and 2 to the x much. That might be the problem. What do you get?
Eric put in the chat natural log of 8.
Well done, Eric. It is. And if you find the first derivative at 0, it ends up being the natural log of 8. Now, if you do the second derivative, you basically get this with another natural log of 8. So the second derivative at 0 ends up being the natural log of 8 squared times 1, which I'm not going to write. I don't think I need to do another one of these. Based on a very small pattern, but it is a pattern I think is easy to detect, what will the third derivative be?
Natural log of 8 to the power of 3.
And if you figure that out, shouldn't you be able to tell me now what the nth derivative at 0 should be? The nth derivative at 0.
Natural log of 8 to the power of n minus 1.
Is it n minus 1 or just n?
It's just n.
Right, just n. So you're done. The power series is this guy, over that guy. Okay, I wish I'd done that one first, because isn't that a much easier pattern to detect? Let me see. I'm going to do this one, but I just want to see if I can find an easier one than that one, because that one's horrendous. No, okay, this is it. This is not fun. I mean, it looks like the others, but trust me, this one is not fun. The value here is 1. That's fine. If you differentiate this guy, you get negative sine x, and the first derivative at 0 is 0. If you do the second derivative, you get negative cosine x, and the second derivative at 0 is negative 1. If you do the third derivative of this guy, you get negative, let's check that, cos gets me, negative, stays put, cosine, you get positive sine x. So the third derivative at 0 is 1. Can you trust me that the fourth derivative at 0, that's nothing, darn it. The fourth derivative at 0, which is that guy, is -1. So positive 1. It goes 1, 0, -1, 0, 1. If I did the next one, it would be 0. If I did the one after that, it would be -1. If I did the one after that, it would be 0, and so on. This is not going to be an easy one to generate the nth derivatives. And I'm actually not going to do the nth derivative because of that. Would you agree that every second term is 0? So you're not really going to be able to create a formula that does zeros and then numbers and then back to zeros, right? That is not a convenient way. So I'm going to cheat. This one is n equals 2. Technically, this is n equals 0. This is n equals 4. This is n equals 6, right? And so on. So far, so good. Do you notice that the answer to whatever I put here at 0 is either 1 or -1? Would you agree that is the number? Now, we know how to do that guy. Don't you get this guy by doing -1 to the n or -1 to the 2n, right? And I am going to find the nth, not the nth derivative, but the 2nth derivative. In other words, I'm just going to create a formula for even derivatives. Which one of these two then would generate these numbers here for the 2nth derivative at 0? Would it be -1 to the power of n or -1 to the power of, oops, n add 1? That's the other choice. Which one would generate 1, then -1, 1, then -1?
N plus 1.
So this fella could be that, right? Well, let's check it out. Suppose I pick n equals 3, then this would become the 6th derivative at 0 should be -1 cubed plus 1, which is +1. Is the 6th derivative +1? No. But if there's only two choices and I figure out one of them doesn't work, doesn't that mean the other one should work? So I can now say that this guy is going to be -1 to the n. Check that out. -1 to the n, yes. Already did the n plus 1. So what's that going to look like as a power series? I'm going to do n equals 0 infinity. I'm going to do that -1 to the n thing. And that. Now you might say, where's all that 2n coming from? Isn't it this 2nth derivative? And the 2nth derivative is this. But if you pick a 2n, isn't the guy that matches at x to the 2n and the guy in the bottom is 2n? And that guy is your power series for cosine. They are just ugly, which is probably why we very, very rarely ever find power series for functions, because some of them are really weird and some of them are just impossible. Right? If you just randomly pick a function like e to the power of cosine x, it's pretty ugly. Try the first 3 or 4 derivatives before you realize there is no clear pattern that any human being could find. So the power series and the infinite power series is impossible. So it's actually quite rare to be able to do the thing perfectly. But of course, that doesn't mean that we can't use it. Can't we just use it by maybe doing it for only the first 4 terms? And remember, when you do it for the first 4 terms, it's not perfect, but isn't it pretty good? Pretty good fit. So I'm going to tell you one. This is the power series. Start again. This is the power series for sin x. It's x, take away x cubed over 3 factorial, plus x to the 5 over 5 factorial, take away x to the 7 over 7 factorial, plus or minus. Do you see it has a kind of nice symmetry to it, doesn't it? The one that we just found is the cosine function, which is 1 take away x squared over 2 factorial plus x to the 4 over 4 factorial, take away x to the 6 over 6 factorial. That's another one that we have. And here's my friend, 1 plus x squared, plus x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so on. Those are very common ones. They're very hard to get, but we just fought our way through that one. Haven't we done this one? That one was pretty easy to do, right? We fought our way through that one. You'll have to trust me on this one. I want you to look at these power series because they actually give us insight into what the heck is going on. Do you notice that the sine function only uses odd powers of x? Do you know the sine function is called an odd function? And you might think, what a strange name. Why are sine functions odd and why are cosine functions even, right? Even functions have a y-axis of symmetry. Odd functions have half-term symmetry. Well, there's a reason. It's because of their power series. If you give me the power series of a function and it's made up of nothing but odd powers of x, I know that function is an odd function. I know that function can be rotated about the x-axis and, it's got a half-term symmetry. If you look at this guy and you look at this guy and you made all of these positive and you added them together, don't you get that guy? If you made all these terms positive and you made all these terms positive and you added them together, you get that guy. That means that in some way, e to the x is connected to a sine and a cosine function. Now, of the 2 functions in the universe that you would pick, wouldn't the sine and cosine function probably be the last 2 that you would ever pick that had any connection to e to the x? But when you look at the power series, can you see that connection is quite strong? If I could make all these positive and make all these positive, right, and add them together, wouldn't I get this guy? And they do have functions that do that. There's a function called the hyperbolic sine function, right? Sine h. It's actually got this power series, but they're all positive. And the hyperbolic cosine function has this series, but they're all positive. And when you add a hyperbolic sine function to a hyperbolic cosine function, you get e to the x. Which means that when we look at functions, we don't actually see everything that's going on. What we're seeing is kind of what we think that function looks like. But when you do its power series, you get so much more out of it. Such a cool process. Well, now that we've got that guy out of the way, let's talk about Taylor's series. Taylor's series is also a power series. It says that provided f of x is a well-behaved function, at least close to x equals a, then its power series can be written as n equals 0 to infinity, the nth derivative at a, not 0 anymore, x minus a to the n, rather than x to the n, all over n factorial. And that's called Taylor's series. Isn't Maclaurin series just a special case of Taylor's series where a equals 0, right, where it's centered at 0? But in the history of things, Maclaurin discovered Maclaurin series first. And then later on, this guy Taylor said, that's really interesting. I wonder if you could create a formula where it wasn't the derivatives at 0, it was the derivative at a. And that was a kind of cool thing to discover. So he managed to get his own name for it. He didn't steal Maclaurin's. He climbed on top of Maclaurin, right, and developed a little bit more, right? And mathematicians are cool with that, unlike that thief Leibniz. Now, what's the kind of questions that you could be given? Well, the question doesn't make sense. I'm looking at this question and thinking, what the heck is it telling me? Okay, now I know. It's a little bit strange to be told this guy. Someone spent a lot of time and figured out for this particular function, the nth derivative at 6 was this guy. Right, so we'll just say, oh, that was nice. We are now going to create the power series using this piece of information. So it's really just plugging all this horrible mess into here and then trying to make it look pretty. Right? So the power series for the function will be sigma n equals 0 to infinity. The nth derivative at a, in this case, it's this guy. Times x minus a to the n. Right, if you tell me the nth derivative at 6, haven't you told me the a is 6? Are you happy about where that x minus 6 is coming from? Right, if this is 6, wouldn't this also, this a here be 6? And that whole thing is going to be over n factorial. Can I just stick the n factorial there because it just looks nicer? Right, style points and you're finished. Is there anything on the top or bottom that can cancel here to make it a little bit simpler?
You can get rid of the n factorials.
And have another look. I can't see anything else, so we're finished. And so you're going to have this guy, and there's your first Taylor series. If you tell me the nth derivative at 0, can't I make a Maclaurin series? If you tell me the nth derivative at 6 or 46, can't I make a Taylor series? So I get initially confused because I was wondering what they were expecting me to do with that information. Okay, yeah, we have time for 10, but I'd keep 10 for a minute if I could. Let's do 11 first. Here is a function. And we are going to create a Taylor series centered at 8. Why can I not do a Maclaurin series for this function?
Not 0.
0 is a bad place, isn't it, to evaluate anything, including logs. So that's the reason. So we're going to go through that same kind of process that we did with all the other ones, right? First, second, third, fourth derivative until we can see a pattern. But now it's going to be evaluated at 8 instead of at 0, right? So that's the main difference. So the function at 8 is the natural log of 8. The first derivative is 1 over x. And if you evaluate the first derivative at 8, you get 1 over 8. So far, so good. Now, if you call that x to the negative 1, when you do its derivative, you get eventually that. Are you okay with me doing all the between here and here in my head? Right? Can you imagine if you turned that and you got that? It just saves a whole load of working if I can do that. Now I'm going to call that negative 1 over 8 squared, not negative 1 over 64, right? But leave the calculation. Now if I do the third derivative, I'm going to get a positive 1 times 2 over x cubed. And the third derivative at 8 is 1 times 2 over 8 cubed. If I do the fourth derivative, I get negative 1 times 2 times 3 over x to the 4. And the fourth derivative at 8 ends up being negative 1 times 2 times 3 over 8 to the power of 4. Now you keep going until you are comfortable that you have found a pattern. I am comfortable I have found a pattern. So we are now going to find that guy. Because once we got that guy, the question's over. So let's forget about that one, right? Those ones, pain in the butt, don't look at them. The first derivative is this guy. The second derivative is this guy. The third derivative is this guy. And the fourth derivative is this guy, right? First, second, third, fourth. You don't need to tell me the whole thing, but do you see any kind of pattern that I can do? Is there anything I can write here? Do you see anything?
You can start with a negative 1 to the power of n plus 1.
Okay, let's check that out. 1 gets you positive. I agree. That's the plus minus done. How about these 8s and 8 cubes and 8 to the 4s? Can you see any pattern here?
Isn't it n minus 1 factorial?
Oh, you got the other one. You got ahead of the game, and she is right. You see what Maggie just noticed? Isn't 1 times 2, 2 factorial? Isn't 1 times 2 times 3, 3 factorial? Do you notice that the fourth derivative only has 3 factorials? The third derivative only has 2. Do you see why the nth derivative has n minus 1 factorial? We are almost done here. What about the 8s that I was talking about now? What is the pattern here?
8 to the n.
Now, we are done because the function is going to be sigma, and yeah, n equals 1 this time. We'll talk about that in a minute. The nth derivative at 8, which is this guy, divided by n factorial, which I'll just stick at the bottom. And then it's going to be x take away 8 to the n, right? We can do a little bit of cancelling here. Would you agree that n minus 1 factorial on the top cancels out with some of the n factorial on the bottom? What's left? Where does it go?
N in the denominator.
Great. 8 to the n is already there, n is there, and then x minus 8 to the n. Are you comfortable with the simplification into the Taylor series? Now, the guy that I did, I started at 1 not 0. And the reason I started at 1 not 0 is, remember this guy f of 8 is log 8, right? That would be the n equals 0. Would you agree the n equals 0 does not fit this pattern? So you just stick it here. Like a little orphan. It can't join the gang because it doesn't look like the gang. But it's still technically part of the answer, isn't it? You need the log 8 if you want to get the right value. So can you see these guys are a little bit trickier? You know, you got 8s and 5s rather than 0s, but most of what we're doing is of the same vein. So I'm now going to go back to the one I deliberately missed because I didn't like the look of it. Now I have to find it. What's question time? We are going to do a Taylor series for this guy. Evaluated, centered at 2. Okay, so if you find f of 2, you're going to get 8 thirds. Okay. If you differentiate this function, you're going to get negative 8 over 1 plus x squared. And the first derivative at 2 ends up being negative 8 over 3 squared. If you do the second derivative, you're going to end up with positive 8 times, actually I'm going to call that times 1 because this one's going to be times 1 times 2 over 1 plus x cubed. And the second derivative at 2 then is 8 times 1 times 2 over 3 cubed. And if you do the third derivative at x, you get negative 8, a 1 times 2 times 3, and you get a 1 plus x to the 4. And the third derivative at 2 is negative 8 times 1 times 2 times 3 all over 3 to the power of 4. Okay, I think I've seen enough here to get a pattern. Right? So try and forget them, they distract me. Here's a 1. The first derivative gets me this. Second derivative gets me this. Third derivative gets me this. I need to know an nth derivative. Now, if you needed to do the 4th, 5th, and 6th, go ahead. It's totally okay. You do what you need to do to see a pattern. I think I can see a pattern. Okay, anybody want to tell me any piece of the pattern that they can see?
N minus 1 factorial.
I hear n minus 1 factorial. I like
No,
the
n
factorial.
factorial. Sorry.
Good. I like your answer. Agreed. N factorial. Right? 3 gets you 3 factorial. You recognize 1 times 2 times 3 times 4 is 4 factorial. When you see that 1 times 2, have you noticed, although I haven't shown you the working, can you trust me that this would be the calculation? Don't write the answer, write the calculation. That's a key here. Right. How about the 3 and the power of 3 on the bottom? What's that going to look like?
3 to the n plus 1.
Agreed. Would you agree in this question, the 8 is a fixed value? It doesn't change. I guess it becomes negative 8 and plus 8, but let's just focus on the 8. So I'm going to put an 8 there, and then I have to put a bracket around that because people might think I mean 8n factorial when I just mean 8 times n factorial. So sometimes you have to put brackets on things, right? Because you could interpret it 2 different ways. Looks like we're only missing now the plus minus, agreed? There are only 2 choices, right? N or n plus 1. Which one does this one?
N.
Can check it out. It does. Now, if I take this guy and I plug it in here, won't we be pretty much finished? So let's find out what it looks like. N equals 0 to infinity. In this case, do you see that little ugly 8 thirds that's up here? It actually belongs to the family, so I can use it. So that's why this time I'm starting with 0, right? If that guy up there had been e squared, right, or log 8 or something, wouldn't I leave him on his own somewhere over here and then just start at 1? So what do we have? We have this fella, 8, this fella, 3 to the n plus 1, and x minus 2 to the power of n. And on the bottom, the whole thing is over n factorial. And this time we get a perfect kill for kill. And our final answer is n equals 0 to infinity. Negative 1 to the n times 8. X minus 2 to the n. And all over 3 to the n plus 1. Are you comfortable with that one? There is a process to these. They are long, but there is a process. Remember, write the calculation down, not the answer. Do as many derivatives as you need until you're comfortable that you can see a pattern developing, right? If you can predict what the next one would be, then you must know what the pattern is, right? That's one way to kind of convince yourself that you're ready to move on. $12 is pretty straightforward. Yeah, I'll let you play with 12. 13's, oh, 13's pretty. I want to do 13. Yeah, let's do 13. So in question 13, we are going to do e to the 2x Taylor series centered at 7. So if I find f of 7, I get e to the power of 14. If I do the first derivative, it's 2 times e to the 2x. And the first derivative at 7 is 2e to the 14th. If I do the second derivative, I get 2 times 2, which I'll call 2 squared, e to the 2x. And the second derivative at 7 is 2 squared, e to the 14. I think I know the answer, but I'll do it one more time. The third derivative would be all of this times another 2, so 2 cubed. And the third derivative at 7 is 2 cubed e to the 14. Are you comfortable that you can see a pattern here? Right. So I'm going to do an nth derivative at 7. So first one gets you this guy, second one gets you this guy, third one gets you this guy. What would the nth look like? Actually, a pretty simple formula, isn't it? What would the nth derivative be at 7?
Should you do the n e to the 14th?
Yeah, isn't e to the 14 fixed? And the 2 to the n guy? I'm just dotting that. Can you plug that into the power thingy and make it look pretty, and you're done? There are a lot of things I haven't done. I haven't found the interval or radius of convergence. You're going to be asked to do that for some of these power series after you find it. But isn't that just the usual ratio test that you're just doing? You know, the usual things after that.